Okay, so we will get started. I believe sorry, is the presentation visible to you? Let me show. I'm sorry, I have some issue connecting across. I'm not able to share the. By the way, are you able to see the presentation now?
No, sir, nothing's visible.
Okay. Some issue here. 1 second. Yeah, is it visible now?
Yes, sir.
Okay, thank you. Okay, I guess we discussed this numerical problem, so we'll continue from here. Please remember that we considered the heat transfer, basically flow with viscosity and heat transfer, hypersonic flow across a flat plate. And in this particular problem, we made use of the correlation, the theoretical correlation between CF root RE and M infinity, the plot that is shown there, which is shown for different temperature ratios. Temperature ratios as in TW by TE. TW is the wall temperature, TE is the temperature, static temperature at the edge of the boundary layer. So for different ratios, the plots are prepared. And what we did was that for the given conditions, we first located the point, the operating point. It's on an adiabatic plate, so we chose the insulated plate option, and that corresponding to the value of Mach number that I guess it came out with 9.295. So we just projected it here, and correspondingly we saw that the resulting value of this parameter CF into R root of REX will be something like 0.242, 4243, etc. And based on REX, we calculated CF. So CF, the non-dimensional shear stress, TW divided by half of V squared. So once we know the value of CF, we can make use of the mainstream velocity and density and calculate the shear stress. So that's how we have got the value of shear stress. So what this helps us do is, given a set of initial conditions or operating conditions, we can identify, or we can calculate the shear stress at a given location. Here the length is given as 0.3 meter. So we could calculate the shear stress at that location. So this is the benefit of boundary layer solution, or boundary layer formulation, and the theoretical solution based on that. Now, so more importantly, this provides insight to some of the factors to be considered in hypersonic vehicle designs. We'll see them. One of them is that, so you can see a plot based on the same solution that we have just discussed. Here, the plot is made between y by x square root of Rex. So it's not this y by x. That is, you have a flat plate. You have hypersonic flow approaching a flat plate. X in the flow direction, y in the transverse direction, and for any given location, we are considering whether the plot is y by x root of Rex. So for a given x, you calculate Re based on the streamwise streamwise coordinate x, and then plot the values against y by x square root of Rex. So y by x, the ratio of transverse coordinate to y, the streamwise coordinate, multiplied by root of Re at that point, at that location. That is on the x-axis. Y-axis. On the x-axis is u by ue. What is u? U is the velocity at any point within the boundary layer. Ue is the velocity at the edge of the boundary layer. So u here, ue at the edge of the boundary layer. So for any location, we can identify u as at some internal point, at some point of some value of y by x, whereas ue is at the edge of the boundary layer at delta. So that's a parameter on the x-axis. So this is plotted for different Mach numbers. As you can see there, Mach 4, 8, 12, 16, 20, etc. So obviously our interest is in the higher, in the hypersonic section of the curve. Hypersonic category of the curves, the plots. So one thing that we can readily observe from it is that with increase in Mach number, the value at which you reach unity for this u by ue, that increases. The value of y by x, y by x into Rex, for at which you reach unity for u by ue, that increases tremendously with Mach number. Say here you can see that I say Mach 12, this is where it reaches. This value may be something like 20, 30, 32, etc. Whereas for 16, the value where it approaches unity is around, say, 50, etc. So then beyond 60, etc. So what it shows is that with an increase in Mach number, there is a significant increase in the y by x value at which the u by ue tends to be unity. Now let's see what is the physical implication of it. What do you mean by u by ue reaching unity, it means that U is equal to UE, which means basically it represents the thickness of the boundary layer. So U by UE is equal to 1 corresponds to a location where the boundary layer is ending. So this is UE. So when you say U by UE is equal to 1, it means that you are at the edge of the boundary layer. Now, so the location where it reaches, so that edge of the boundary layer, that is the y by x corresponding to the edge of the boundary layer, keeps increasing. So that's what it means. So for as you go downward, as you go upward in the Mach number range, the number at which, or rather the range at which, or the value at which y by or the U by UE reaches unity, that is the thickness of the boundary layer increases. So the observation that U by UE approaches unity at higher y by x means the boundary layer is thicker. That is, with increase in Mach number, there will be a significant increase in the boundary layer. So boundary layer thickness. So the boundary layer thickness increases with increase in Mach number, and this is an observation of practical interest because it means that the viscous dissipation is going to be more tremendous. And the actually we in the initial classes we have discussed about the viscous interaction, etc. So that is where the boundary layer starts interacting with the free stream flow because it keeps thickening. So that is one of the major observations that can be drawn from this theory. Now, about the temperature profile, this we have discussed already. I'm just showing a theoretical graph also. We had examined when we examined the thermal boundary conditions, we had considered this option, this kind of a situation where you have some you have a lower Mach number in the at the wall. You have a lower wall temperature or lower temperature at the wall. You have a low temperature in the free stream, but in between, somewhere in the boundary layer, the temperature becomes high. And I had shown the corresponding CFD simulations. You have low temperature, this bluish region here, thick blue region in the free stream where the static temperature is very low. But in between, inside the boundary layer, you have a region of relatively high temperature. Okay. And this is indicative of viscous dissipation of kinetic energy within the boundary layer. So part of the kinetic energy gets dissipated, gets converted to thermal energy, and that is the region dominated by that diffusion is, or rather that dissipation is where you will have higher internal energy and higher static temperature. So this y by x root rex also is reflective of this variation. So what you have here on the x-axis is T by Te, and this kind of a profile is indicative of the viscous dissipation within the boundary layer, and that also increases with Mach number. So you have Mach 4, 8, 12, 16, 12, 20, etc. So the viscous dissipation also of energy to kinetic energy to thermal energy also increases with increase in Mach number. So that's another observation which comes from this analysis. Now, closely related to this is the concept of recovery factor. I'll try to explain that. Recovery factor means let's consider again a flat plate. You have a free stream coming at a high Mach number. Now, we know that there is the static temperature is going to vary across for a given inlet conditions. The free stream static temperature, which is a function of the Mach number, the free stream static temperature is going to be lower, but at the wall where the boundary layer, the flow comes to rest, the velocity is 0. So the velocity is 0. So the Mach number, or rather the temperature will come out to be close to T0. If you have an adiabatic wall, in which heat is not lost at all, it means that at the wall you will ideally have the value of T0. That is, if the flow is coming at Mach 10, And if the free stream static temperature is say something like 200 Kelvin, then the stagnation temperature or the temperature near the wall is going to be close to T naught, T into 1 plus gamma minus 1 by 2 into 10 squared, right? T into 1 plus gamma minus 1 by 2 into 10 squared. So 200 into 1 plus gamma minus 1 by 2 into 10 squared, since 10 is the free stream. So Mach number. So the entire flow, the kinetic energy will be converted to the internal energy, and when V equal to 0, that is at the wall, if the wall is adiabatic, you will have T naught is equal to the theoretically calculated, or the temperature be, the wall temperature will be equal to T naught, which is theoretically calculated. But in reality, this does not happen, because this deceleration doesn't take place without energy loss. So when we say that the stagnation temperature or the wall temperature becomes stagnation value, it's by assuming that the entire kinetic energy is converted to thermal energy, which doesn't happen in reality. There will be some dissipation within the boundary layer, etc. So because of that, a part of energy will be lost. So a parameter which quantifies how much of this is recovered, or how much of the internal energy is recovered or retained as internal, how much of the kinetic energy is retained as internal energy, a factor which represents this is called recovery factor, and it is defined as H here indicates enthalpy. So enthalpy of an adiabatic wall minus static enthalpy at the edge of the boundary layer divided by stagnation enthalpy minus the static enthalpy at the edge of the boundary layer. I'll explain it further in terms of temperatures. Please remember that this first expression for perfect gas, since H is nothing but Cp into T, and since Cp is constant, the recovery factor becomes equal to TAW minus TE divided by T naught minus TE. I'll try to explain this again. TAW, the adiabatic wall temperature. That is, we are considering the wall to be adiabatic. So if the wall is adiabatic, there is no energy lost to the wall, which means that the resulting temperature at the wall should be theoretically equal to T naught. But in reality, it does not happen. So that's why we treat it as a separate parameter, TAW. This minus the free stream value TE. So a free stream, that is edge of the boundary layer, that divided. So this is the real resulting temperature, TW minus TE, resulting temperature difference. But the actual temperature, or the ideal temperature difference in the absence of such losses would have been T naught minus TE. Why? Because at the wall the velocity is 0. So if there is no loss, you expect the temperature to be equal to stagnation temperature. So T naught minus TE is what you expect. TAW minus TE is what you get. Okay. So this ratio between the two is called recovery factor. Recovery means how much of the internal energy is recovered without loss, without being dissipated or lost by other means. So TAW minus TE by T naught minus TE is called the recovery factor. Okay, and typically for most of the flows, it can be approximated in terms of Prandtl number. Remember, Prandtl number is mu Cp by K. Mu Cp by K. So this recovery factor, it has been found to be actually empirically as well as theoretically. Okay, this is an approximate relation, but a very convenient one, because just by knowing the fluid properties, mu, Cp, and K, you can calculate what is going to be the recovery factor. So, though it is somewhat of an approximation, it's a very useful relation, very useful approximation for calculations. So, recovery factor is approximately equal to square root of PR, Prandtl number. Okay. So I hope the concept is clear. If you have any question, I can explain it further. Please remember recovery factor as a parameter which represents how much energy has been, internal energy has been retained as the temperature without being lost or without being dissipated in the stream. Any questions on this part? Recovery factor? Okay. If not, we'll look at another numerical problem. This involves heat transfer also. So please remember what we did earlier was with respect to uh, momentum transfer, or rather shear stress. So was purely related to the calculation of shear stress. But then we have seen the definition of Stanton number. We have seen how that relates the shear stress to heat transfer. We have seen Reynolds analogy, and we have seen that momentum transfer is analogous to heat transfer under the conditions of boundary layer analysis. Okay, so now what we are going to look at is next is how we can calculate heat transfer. So in this problem, what we did was we calculated the shear stress based on the theoretical analysis. What we are going to look at next is how we calculate the heat transfer, because keep in mind our focus of attention is heat transfer as well as momentum transfer. Momentum transfer in terms of in the presence of viscosity. So shear stress we have seen how is used, how it can be calculated. Now we'll look at heat transfer aspect of it. Before that, just be reminded about the definition of Stanton number, CH, usually shown as denoted as heat transfer books usually use ST for Stanton number, but gas dynamics books seem to use CH for some reason. CH, Stanton number. Okay, and remember we have seen the definition as the ratio of heat transfer by convection to the thermal capacity of the fluid ratio of heat transfer by convection, that is H, Newton's heat transfer coefficient, H into TW minus T infinity, that is a heat transfer flux by convection, and the thermal capacity of the fluid, rho Cp V infinity, of course divided multiplied by A. So the ratio between the two is referred to as the Stanton number. So heat transfer by convection divided by thermal capacity of the fluid is the Stanton number. And we have seen that it can be plotted the same way as the shear stress parameter. So Cf root of Rex, here it is Ch root of Rex. We have seen details of this curve. So that's what we are now going to make use of for solving heat transfer problem. Consider statement is similar. Flat plate exposed to hypersonic stream at the Mach number is the velocity is given 3,300 meter per second under ambient conditions of pressure 1,800 Newton per meter square and temperature 2010 Kelvin. So the outside conditions are given, the static temperature as well as atmospheric pressure. Static pressure are given as 210 Kelvin and 1,800 Newton per meter squared respectively. Now the total length of the plate is 0.9 meters. What we are required to calculate here is shear stress at a section of 0.25 meter from the leading edge. So I'm sorry, if this is the plate, the total length is given as 0.9 meter, and what we has as X, the location where the calculation has to be done, is 0.25. What is to be calculated? Calculate the shear stress there and also calculate the heat flux at that location. So at this location, what is tau, the shear stress experienced at the wall, and what is heat transfer to the wall is what is to be calculated. An additional information is that the temperature is the wall is maintained at a constant temperature of 210 Kelvin, which means that by some means, heating, cooling, whatever it be, the wall temperature is maintained at 210 Kelvin. That is, it's a constant temperature wall. So TW is specified as 210 Kelvin. Okay. Now let's as we have just reviewed what we did for the shear stress problem, let's try to relate the situation to what is given here. If you look at the two curves, again the physics of it is shown on the two sketches on the top side. On the left hand side, the familiar sketch that we have been using to calculate to represent the flat plate problem, On the right hand side, you have the zoomed in view of CFD simulation of the temperature field. And we have a similar situation here where you have a specified wall temperature is given. That is, here it is 210 Kelvin. Okay. So now let's look at the two pictures that we have familiarized already. In the first, this is the first one is what we used for calculating shear stress, where we made use of CF root x. We calculated root REX. We calculated RE from the given conditions. We calculated and then we know what is M that is given, and we correlated the point from based on M, and then identified the value for the parameter CF into REX. The same way we did there, we will proceed in this case also. So here, what we need to find out is CH square root of REX corresponding to the given condition. The free stream conditions, temperature, velocity, etc. are given, so the Mach number can be determined. Once you know the Mach number, wherever it comes to be, I'm just drawing a line here. What we need to do is to draw a vertical line to a curve which has TW by TE as 1. TW by TE as 1. Why do I choose this curve? Because it is mentioned that the free stream temperature, air temperature is 210 Kelvin, and the wall temperature is also 210 Kelvin. So TE is equal to 210, the free stream temperature, and TW is also 210, right? So TW by TE obviously is unity. So that's the reason why I choose this graph where TE by TW or TW by TE is given as unity. So what I need to do is wherever I drop this vertical, I should project it to that TE by TW equals 1 graph, and then then project it horizontally to get the value of CH root of REX. From that, substitute for REX, calculate the value of CH, and then from CH we know is a ratio of heat transfer divided by thermal capacity. Thermal capacity is a that can be calculated as we know the CP for air, etc. So once we know the value of that, we can calculate what is the heat transfer. So that is going to be the approach, and you can I just given all the steps here along with the values. You may please check the calculations. I'll just go by the steps once again. The given values, the free stream values, etc., are shown in these curves. The yellow shaded columns show whatever is calculated. For example, M infinity is calculated based on velocity and the static temperature. That comes out to be 11.36. And rho is calculated based on P by P and P, R, and T, P by RT. Okay, and then RE, rho VD by mu, is calculated based on mu, which has been taken from the tables. So this is made use of to calculate Reynolds number. So once we have REX and once we know M infinity, then CF multiplied by square root of REX can be taken from the graph. So say here, Mach number comes out to be 11.36. So I need to draw a line, say somewhere here, 11 point whatever. So somewhere here, and it goes to the I should intersect the TW by TE equals 1 graph, and then see what is going to be the corresponding value of CH divided by square root of REX. And for this case, I guess I didn't. If you hopefully, if you draw it correctly, I guess it comes out to be 0.43. That is CF square root of REX comes out to be 0.43. And we can estimate REX by rho VD by mu as rho VD by mu, and you can calculate CF and TAW, the adiabatic wall temperature, can be calculated based on the I'm sorry, here the not the adiabatic wall temperature, here the shear stress can be calculated as we did in the first case. In the first case, using CF. So if CF is known, then the shear stress can be calculated. Now the next part is the heat transfer calculations, for which we know the value of TW, which is given as 210. So this is already given. So TW by TE is 1 and CH root of square root of REX from the chart. Yeah, that comes out with 0.54. I stand corrected. I think I said something else. So if you plot corresponding to 11 point whatever that Mach number, the value comes out to be something like 0. I think it comes out to be 0.54. The value of that comes out to be 0.54. Or what I've written here is 0.54. Please check that whether that is correct or not. Anyway, I'll just explain the steps. So that gives us now RE is already known, so you can calculate the Stanton number. So once you know the Stanton number, then we can calculate H because Stanton number is H into the, here I have the relation here for the heat transfer calculation. The convective heat transfer is Q is equal to H into TW minus TA, the free stream value, TW, the wall temperature, and T infinity, actually is T infinity. So that's what gives us the the heat flux. So now once we have this parameter, the next is to calculate the recovery factor. Recovery factor we know is TAW divided by TAW, that is adiabatic wall temperature minus TE divided by T naught minus TE. So adiabatic wall temperature minus TE divided by T naught minus TE. Okay. So the question here is what value will I use for? So if I know this value of recovery factor, then from this I can calculate the adiabatic wall temperature because I know T naught, stagnation temperature, because static temperature and Mach number are given. So stagnation temperature can be calculated. TE is given as 210. That is given, so we can use it. What is required to be calculated here is the adiabatic wall temperature, because that is one which is required for heat transfer calculations. So to calculate that, I need the value of R, the recovery factor. And recovery factor, we know that can be estimated or can be approximated as square root of PR. And PR for air, I mentioned it earlier, can be calculated, taken as 0.71. For air, the Prandtl number mu Cp by K comes out with 0.71. So we can just assume that to be a constant and use it as in this context. We can get the recovery factor. Once we have the recovery factor, we can calculate TAW as I just mentioned here, because T naught is T naught comes from T and the Mach number, static temperature and the Mach number. And so once we have that, the Q can be calculated as H into TW minus T naught. H into TW minus T infinity. Okay, so that's how we calculate the heat transfer. So what we are doing here is that just by using the free stream conditions and using the theoretical correlations available based on the boundary layer analysis, we are able to calculate the heat flux. We are able to calculate the shear stress. We are able to calculate the heat flux. So this is the benefit of, or this is the end goal and objective of boundary layer analysis, that is to be able to calculate shear stress and wall heat transfer based on the free stream conditions. Anything to be explained further? Okay, we'll just proceed further. In the related to heat transfer, I just need to also state about the stagnation point heat transfer also. So today I'll just complete with this. Stagnation point of a blunt body surface. If you consider the blunt body surface, this part is sort of obvious to us by now. That is, if you consider as you see in this sketch, a body with a blunt surface that is and exposed to high Mach number flow, you will have a detached shock. So this region where which is adjacent to the stagnation, which is actually nearby the stagnation point, is referred to as the stagnation point region. Okay, so when we consider heat transfer, now it is certainly unique because that is a place where you have the flow impinging with the highest momentum, because it's there where it is hitting directly on the body. So the heat transfer that we spoke so far is for a flat plate. Now, some of the simplifications can be extended or adapted to situations like this, where you have stagnation point heat transfer. So we'll just see what is the implications more than the theoretical formulation for that. The main thing is that we are carrying forward the similarity analysis. Instead of the boundary conditions, we are boundary layer conditions. We are going to use an approximation where the velocity at the boundary layer, edge of the boundary layer is going to be considered to be low, and the temperature is going to be high. The reason for that is here, say it comes after a normal shock, right? The stagnation point region, it comes after a normal shock. So the flow goes down to subsonic, and also near the wall, it's due to boundary layer effect, is going to be even lower, which means that the velocity in that region can be, that is considered, I mean, in comparison to the free stream flow. That is important. So we are considering high supersonic flow. So free stream velocity is very high. After the normal shock, you have subsonic velocity, low subsonic velocity. So we can neglect, or the velocity there in that region adjacent to the wall can be considered to be smaller. At the same time, the static temperature, static enthalpy is going to be high. So because of these two factors, the parameter UE squared by HE can be sort of neglected within that region. So this is one of the simplifications which will lead to some relation. Like just skip this part. We also get back to a one-dimensional equation, governing equation, one-dimensional equation, which is of not one-dimensional equation, an equation, ordinary differential equation. So that can be further solved by using the relation for velocity gradient from Euler's equation, and also by adapting the Newton's theory that we have discussed earlier. We skip all that derivation part, but the relation comes out to be what I'll just highlight what is required for this discussion. The du by dx can be equated as, what is du by dx? It's a rate of change of the edge velocity with respect to x direction. So the variation of velocity gradient, or rather the presence of velocity gradient along the x direction. Now that can be expressed in terms of 1 by r square root of p minus p infinity divided by re. This 1 by r is the radius of curvature. Remember, we are considering a body with a curvature. So r here indicates or represents the radius of curvature. So in this case, for example, so if I am considering this region, I'm sorry. So the radius of curvature is what is used as r here. So what it shows is that this relation, this is the relation, the solution for the ordinary differential equation, which shows that QW, that is the heat transfer at the wall in the stagnation region, can be expressed in terms of several parameters, but most importantly, square root of du by dx. But this du by dx by itself can be equated as 1 by r into root of 2 pe minus p infinity divided by rho e, which in turn means that all other parameters being the same, the heat transfer at the wall is inversely proportional to 1 by square root of r. That is, when you have a higher radius, you will have lower heat transfer, and vice versa. If the wall radius or the radius of curvature is very low, you are going to have high wall heat flux. Now, this is a very important, actually, this, I guess this formulation was done when NASA was toying with the idea of space shuttles. And this revelation, actually, that this theoretical conclusion was a major step in their advancement of the designs, particularly for ballistic ships, where it came as a revelation that the heat transfer at the wall can be reduced if you use a high radius of curvature. And that's the reason why the nose radius, there is a strong tendency to use large blunt nose when you have hypersonic flows, or when you have the body being exposed to high heat transfer rates, as in the case of re-entry vehicles. So re-entry vehicles, this kind of shapes are familiar to us. See the surface, they're highly flat. Actually, that's it means high, I mean, there's a curvature and the radius of curvature is very high. Whereas the initial thinking, or initial more probably it was more intuitive to have sharp noses like this. But then this analysis and experimental observations, etc., led to the revelation that if you have such sharp corners which with lower radius, the temperature, the heat flux at the stagnation region is going to be very high. So, and that's the reason why people moved from this kind of shapes to more flatter, or shapes like with a larger nose radius. So that's the reason why blunt bodies are used so frequently in hypersonic flows, particularly when there are higher the chances of higher heat transfer at the leading phase. Okay, with that I keep quiet now. Can I request the teams, remaining two teams, to quickly present their assignments? I guess team 1 and 2 have presented already. So 3, 4, and 5. I don't know whether people are around, so let me try my luck. I'll just try calling. Rajashri, Rinish, Sanjita, Sanjay, Raghavendra, all belonging to third group. Any of you present, or all of you present?
Yes, sir.
Rajashri is there. Yeah. Others are there? Rajashri, you have the presentation. Can we just see the slides?
Yeah, can you give us 2 minutes, sir? The person who's supposed to present is not available today. So,
Ah. Can you please request him to be available in the next class?
yes, sir.
Yeah, please. Okay. So I just leave it as your responsibility to make sure that it gets presented next class. Is that okay?
Yes, sir. I'll make sure she comes.
Thank you. So that's about 3. 4. Sanjeev Shyamala is there. I guess Sanjeev also is here. Surya Swaroop. Can you please, if you have, please present or tell me how you'll go about it. Sanjeev Shyamala, please. Sanjeev is there. Shyamala was there, I guess. Can you please respond on this? Hello. No response. Then we'll go to 5th. Yuvraj, Shashank, Sam and Sahana. Anybody, please?
Am I audible, sir?
Yes.
Yes, sir. Just a second.
Yuvraj, yeah, you can please share and then.
I hope it's visible, sir.
Yeah, please.
And this is assignment 3 from group 5, and we were given a flight data, which is shown here, and our alpha angle of attack was 38.4 degrees. And using this relation, we compared the flight data and the one with the theoretical relation. So we almost got a similar or a kind of similar graph for which is holding good for both. So we infer that both the theoretical and the flight data are holding good till 0.8, and then this CPS is the XYL graph for alpha equal to 3.8 degree and alpha equal to 19.2 degree. Here we can infer that as alpha increases, the CP value increases.
Sorry, I didn't hear that. When alpha increases?
The value of CP increases.
Increases, yeah, fine, okay.
So these are the inference.
What do you attribute? Actually, somebody had asked that earlier also. I think everybody has observed it in the first slide. Why do you think there is a difference towards a trailing edge?
Training. Yes, I guess you were explaining it as like due to the wings
Most
or the
probably because,
tail of
yeah, most probably because of geometry variations in the real flight.
Yes.
Okay. So any additional inference that you are making in the last slide? Sorry, go to that. What were you stating there? Last slide, yeah.
Yeah, that's it.
That's all right. Yeah.
Typical.
Okay. Okay, that's fine. Yeah, fine. Okay. Thank you.
Thank you.
So the remaining two groups, 3 and 4, I would request them to present it in the next class. Okay, then. Thanks to all of you. Bye.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thanks.